Here's a kind of complicated RC circuit. Got a battery, resistor, and a capacitor, and a little loop here, but then we have a switch here. And then on the other side of the capacitor is a branch with some resistors in series and parallel, and then another capacitor right there. So we have a lot going on here. Let's see. So the first question is, how much current flows from the battery in milliamps with the switch open? So remember, whenever we say flows from the battery, that means the total current. Right? So just how much current flows from the source with the switch open? And the answer to the first one is just 0. So 1 is 0 because, if there's a switch in the middle, there might be some path where current could make it out of and back to the battery. But if you put a switch right there, there's nothing getting back to the battery. So there is no closed path where current could actually flow. So it's 0. Or if you really need to do this mathematically, you could put a resistance of infinity right here. And then whatever you add up from all that junk, it's going to be in series with something with an R of infinity. So the voltage, no matter what voltage you apply, the current would be 0. But basically, open, no current. Question 2. What current flows from the battery in milliamps immediately after the switch is closed? So 2. Immediately. So I'll say this in many problem solutions because these are meant to be detailed. But immediately means the capacitors are discharged. And if the capacitors are discharged, they act like wires. Right? The capacitors are discharged, they act like wires. So if we look at this, then read it again. What current flows from the battery immediately after the switch is closed? So then if these are acting like wires, you just have a resistor network here. You have current flowing here, this in series with this branch. This is just a wire, and you just start to figure it out. Let's see. So what we need is our equivalent. Okay? So it starts with a resistor that's clearly in series. Nothing is branched yet. So we got to flow through this resistor. Everything flows through there. So that's in series with whatever else there is. So 5 k ohms. Plus, now we got to treat this big branch. Okay? This is just a wire. So we say plus this next thing in series is a bunch of stuff in parallel. So to figure out what all this stuff is, we'll make a little parallel branch there. And we'll say, let's see, this is acting like a wire. So this one is 1 over 0.4. All right, now I'm going to do this in kilo ohms. So 1 over 0.4 here, that's a wire, so that's 0. So we don't worry about that. 0.4 plus 0. 1 over 9 plus 12 kilo ohms is 21. Plus 1 over 21. And we could keep going. What about this being a wire? Just because something is a wire doesn't mean you can ignore it, right? If this is acting like a wire, what is it doing? Well, there's a few ways to see it. Physically, you could say, if it's acting like a perfect wire, it's holding these two potentials to be the same, because that's what wires do. Perfect wires keep the potential constant. If these two potentials are the same, no current's going to flow over here. So you'd say, well, this should all be gone. How do we get rid of it mathematically? Well, we acknowledge that this is a branch of the circuit. And what is its resistance? 0. Okay. If you really want to see it mathematically, you do it like that. 1 over 0 plus 1 over 21 plus 1 over 0.4. Well, when you add those up, 1 over 0 is the biggest, right? That's infinity. So the sum in here, because this is infinity, and what's 1 over infinity? 0. Right? So the equivalent resistance of this whole branch is 0, because basically this wire shorts it, at least immediately after the circuit, the switch is closed. It gets shorted out by that capacitor. So really then the equivalent resistance is just 0. This is all 0. The equivalent resistance is just 5 kilo ohms, because that whole thing is 0. So then you just, Ohm's law, 30 equals I times 5 kilo ohms, 30 volts, and you get the answer, 6 milliamps. 6 milliamps. Let's see. Let's do now the opposite, and let's get the current. It says from the battery a long time after. 3, long time. And we'll say then the capacitors are charged. And what does that mean? They act like broken circuits. Act like or we'll call open circuits. Basically means something that's not connected. All right, let's see. So how much current is going to flow? Well, in a simple circuit, no current would flow because the capacitor isn't allowing any current to flow. But this isn't a simple circuit. So you can look at this and say, okay, that's not a path anymore. That's not a path anymore. Current can't flow there and there. But you can see it can still flow there. Right? This has been closed for a long time. So basically you have a simple case of 5, 12, and 9 in series. And I know they're in series because the current never has to make a decision to go there, right? Through the 5, through the 12, through the 9. These branches are all meaningless now because there's nothing going there. So it's really just 30 volts is I times 5 plus 12 plus 9 times 26 k ohms. Whatever that is, 1.15 milliamps. Yes. That wasn't a drop the chalk moment. I just had to go get this. Okay, so now let's erase to do question 4 here. Question 4. Question 4 is, what is the charge on the 20 microfarad capacitor long after the switch is closed in microcoulombs? Okay, where is it? There's the 20 microfarad capacitor. So we know that the charge on a capacitor is the capacitance times the potential difference across capacitor. And when you have a simple RC charging circuit, by the time it's charged up, the capacitor is getting the full potential difference of the battery. Okay. What is the charge long after the switch is closed? Right, okay, sorry. Yeah, usually it gets the full EMF of the battery. But in this case, we have to look at it and realize that it might not get the full EMF because current can still flow here. Right, if it were just these two, it would get the full EMF of the battery because the current would be driven to 0. You'd get no current flow through this resistor. Therefore, this would be at the high EMF, 30 volts. This would be at 0. It'd get the full 30. But since we have this branch, and since current can continue to flow through this branch, you will get a current of potential drop here. So basically, the 20 microfarad is not getting the full EMF. 20 microfarad does not get full EMF due to current flow through that branch we just thought about in the previous part, through the 5 to 9, 5 to the 12 to the 9. Okay, so if it doesn't get the full EMF, well, what does it get? Well, you figure that out just by looking at where it's touching, right? It's touching right here. So really the question is, what voltage drop do we get after 5 kiloohms? Right? So it gets what? It gets the full EMF minus delta V of the 5 kilo ohm resistor. So what is the potential across the 5 kilo ohm? Well, a few ways you could get it. One is you could do what we did in the last problem, and you could get the current through this loop, right? And you could say 5 kilo ohms times that. Or you could use something called a voltage divider. If you ever have a bunch of resistors in series, and you want to know the drop across any one of them, it's just the drop across that one is the 5, that one's resistance over the sum. So delta V, if you're doing this problem by itself and hadn't already calculated the current, it would be 5 over 5 plus 9 plus 12 times the EMF. That's another way to get that voltage drop. Or if you could look at this and say, I don't know, the voltage drop across the capacitor is equal to these two. So the real voltage divider I want to do is delta V across the 20. I'm just giving you multiple strategies here. I'm not saying you should go through every one of these. 9 plus 12 over 5 plus 9 plus 12 EMF. So many ways you could do this problem. Okay. Once you do all that, you're going to get, though, that the voltage across the capacitor is 24.3 or 24.2 volts about. So therefore, the charge is the capacitance 20 microfarads times 20, what was it, 4.2 delta V across the 20 right there. And then you'll have the charge, which comes out to 485 microcoulombs. It's equal to that.